So now we'll discuss about the forward chaining algorithm. Okay, the forward chaining algorithm. So this algorithm is sound. Okay, every inference is just an application of modus ponens, and it's complete as well. So it will eventually derive every entailed atomic sentence. Okay, every entailed atomic sentence. So if you remember modus ponens one more time, let's see. Modus ponens is kind of based on the let's say if A implies B and we know that A is true, then B is true. So that is modus ponens. Okay, so this forward chaining algorithm uses modus ponens, and it starts with some known facts. Okay, start with all known facts in an agenda. So these are like something like our given information. You can say that these are like knowledge based sentences. You can say these are a set of horn clauses. They are actually all those statements are correct. And now if you see, so the known facts are this. So I have already shown you that these are like facts because they are by themselves. So that means they are true. So this means that A equal to true, and this also means that B equal to true. Okay, so they are true. So we have to start with the known facts, and then we have to try to prove something. And what we are trying to prove, so we are basically trying to prove that P implies Q. Okay, so this one, basically this is something we are trying to prove. Now how we prove that? We start with A and B, as I said, that because we already know they are true. So we start with A. This is called an AND OR graph. Okay, it's an AND OR graph, and this is AND OR graph, and we start with A and B because we know they are true. And then we see, is there any rule I can apply directly on that? And then I see, yeah, if A and B are true, then I can say A and B implies L. You see, it's a simple if-then rule, and then A and B is true, so L is true. So this is L, so now L is true. Others have not yet verified. Okay, so if L is true, once we have that, then rule 3 can be applied. You see, so this is basically rule 3. Okay, B. So 1, 2, 3. So this is 1, this is 2, this is 3, this is 4, this is 5. So initially apply rule, or maybe the other way. Maybe let's say this is 1, this is 2, this is 3, this is 4, and this is 5. Okay, so that's better. So now you see A and B. We have applied that. Now see, rule 3 will apply because we know B is true, and now we have already shown L is true. So now from that we can derive M. So that's exactly happening from L and B. We are deriving M to be true. Okay, I am applying rule 3. So by so now then we can apply L and M implies P, which is the rule 4. Okay, rule 4 we apply, and we get L and M because M is true by rule 3. So now L and M together, they will give me P. Once I know that P is true, then P implies Q will also be true. Okay, so gives us, so finally P implies Q gives us. So by forward chaining, we have already derived Q. Okay, our query. It's like a chain reaction, right? So that's why it's called a forward chaining. Each new fact triggers more rules. Whenever we proved M is correct, then it triggered the next rule. So you see, each rule, each new fact, which the fact means that M is true or P is true or L is true, triggers a new rule. So so here we can say that from A comma B we derived L, from L we derived M, from M we derived P, and then from P we derived our goal, which is Q. So the forward chaining algorithm keeps a list or agenda of known facts. Okay, whatever is known, the agenda of known facts, and each time it processes one, it checks which rules depend on that fact, right? Once we know L is true now, then we see what rules are depend on the fact. We see, oh, this rule depends on the fact. Then we can apply that rule. Okay, so when all premises of a rule are known, that means when B and L are known, then only we can deduce. Its conclusion, it adds to the agenda. So agenda will have gradually, initially AB, then we add L, then we add M, and then we keep checking which rule have the premises which are already in the agenda to be true, and then we apply that rule to find out what will be the conclusion, and then we add the conclusion to the agenda again. So that's the forward chaining algorithm. And as said, this is basically sound. So every inference is just an application of modus ponens, and it's complete as well. Okay, it will eventually derive every entailed atomic sentence. So after forward chaining, we have the backward chaining algorithm, which actually operates in just the opposite way. Okay, forward chaining starts with data, backward chaining starts with a goal. Okay, so we'll start from Q and then we'll go back. Okay, we'll start from Q and then we'll go back. So this is the point we start. Or let's say I take a different color, maybe so I'm checking if I have another color. So let's say this is a purple color, and so we start with that item, and then we continue backward. Okay, so how we go backward? So it asks, what do I need? Why do I what do I need to prove this? Like to prove Q, what I need? Then you say, oh, to prove Q, I need P. Then for P, what I need to prove? I need to prove L and M. So this is the way it goes backward. So if we want to prove Q, we look for rules that conclude Q. That's this one. Okay, P to Q. Okay, so this rule. Then we ask, can I prove P? At this stage, we are asking, can I prove P? So then we are, to prove P, we find rules like L and M. So this is a rule to prove P, L and M, so implies P. Now that breaks into smaller sub goals, okay? Like we have to separately prove L and separately prove M. So these are the sub goals, okay? Sub goals. So if you can separately prove them, so then, so until we reach down, so this will kind of take us down the other way, like this way we did. So let's say now there's a backward, right? From Q, we go to P. From P, we see, okay, we need M. For M, we need L. In that way, we kind of go back until we find out that, oh, we need AB. Okay, but AB are facts, right? So, so these are known facts, right? So that's actually helps us to evaluate that, yes, okay, they are correct already. So when we reach to the A and B, so we know that all sub goals succeed. So the main goal Q is proved. So this is a similar kind of graph can be used for backward search. It's also called and or graph. So backward chaining is a goal-directed reasoning. Okay, backward chaining is what? It's a goal-directed. Backward chaining is goal-directed. Okay, goal-directed. So this is very important. Goal-directed. So we start from the end and come to the front. So it's efficient for answering specific queries because it only touches the relevant facts and rules. So you don't need to do or operate on every rule. So you only care for what you are trying to prove and what rules are containing those literals. So it only touches the relevant facts and rules, not the whole knowledge base. Okay. So in summary, forward chaining is data driven. Okay. Facts trigger and new inferences. Okay, facts trigger new inferences. So forward chaining is data driven, right? Data driven, and backward chaining is goal driven. Okay, so backward chaining is goal driven, right? So both are sound, complete, and linear in time. You can see that there's just step by step. You as many number of rules, as many number of as many number of evaluations. So these methods form the basis for logic programming. Remember that, and AI systems that can think in simple rule-based ways. Okay, so these are simple rule-based ways for thinking.